Hello, we're going to do some problems here in section 4.1. So here we're starting a new chapter. I'm sure you might be happy about that. The third chapter was quite tedious. So we're going to be working with Laplace transforms and inverse transforms. And this is a very powerful technique that will be used extensively in your future. So here we have it. Okay, so I'm going to try to find the Laplace transform of the cosine of t using the definition. This is number 4 in our assignment here. So that's what you're doing. I'll just sort of tell you what I'm doing as I go through the page here. So here's the definition, basically, of the Laplace transform. Let me make this a little skinnier right in here. Okay, so I should script L, the Laplace transform of cosine. So first what we'll do is we'll use integration by parts to try to figure out what this integral is here. And that's what you're seeing here. This should look extremely familiar from your days taking calculus, so you can follow through and decipher what I've done here. I've basically substituted, I've chosen the cosine of t right here to be my function f, and this g prime of t to be the e to the minus s of t. Then, of course, we have to find the derivative of the cosine here, and we have to anti-differentiate g to pick an antiderivative here. And then we use integration by parts to find another expression for this integral that we're looking for. As we see, we have another integral that looks suspiciously similar to the first one, and as we have done, or you have done, I presume, in the past, not in this class, but you have studied integration by parts. And we must apply that again with the hopes of trying to find an antiderivative. And that's what you're seeing here and here. So finally, we get an expression. If you look at this expression, I'm going to underline here, we get an expression that where we can actually solve for the integral that we're looking for. That's all. Yes. Okay, I've done some algebra, and so here we have it. That finally we see that the integral of e to the minus s times t times the cosine of t dt is given by this expression right here. Now we will use the definition of what this integral is. That is, it's the limit as b approaches plus infinity of the definite integral from 0 to b of our function that we're integrating, and then using our calculation above, by integration of parts, I substitute, and using the fundamental theorem of calculus here, okay, and then we actually apply the fundamental theorem of calculus here, and we notice that, in fact, as b approaches plus infinity, this term here goes to 0, since s is greater than 0. And this term here goes to 0, since s is greater than 0. So the only thing that's left over is this term. And we just calculate the sine of 0 as 0. The cosine of 0 is 1. And this leads us to our Laplace transform of the cosine of t. Okay. So that's using the definition, and we'll need to be able to do that. But here we have another question where we're going to use this nice table that is provided for us on page 271. So the name of the game in this chapter is to essentially try to understand solutions of differential equations after transforming the differential equation into an algebraic equation via the Laplace transform. So here we're given a function, and we would like to find its Laplace transform. And this is just looking on page 271 in your book. You can see that if you take the Laplace transform of the sum, it's a beautiful thing that it's a linear transformation, and that means that we can find the Laplace transform of the first term plus the Laplace transform of the second term. And this is directly from, directly from our chart you just look up in the chart and see that the Laplace transform of the sine of 2t is given here, and the Laplace transform of the cosine of 2t is given here, and lo and behold, that is our Laplace transform. So this is just an exercise in using a chart in the book and understanding that the Laplace transform is linear. Now, on the other hand, we will want to be able to find the inverse Laplace transform of certain algebraic expressions, and that's the exercise number 25 that I'm going to show you that is done. So we're trying to find, so here we're given capital F of S, and we would like to find f of t. The convention is that the inverse Laplace transform of f of S is little f of t. So we're looking for little f of t. Okay, so what we have to do is we again look at our chart, and we notice here that what comes into play is the gamma function, which is a beautiful function, which is mentioned in this chapter. We're not going to get into it that extensively, but it's you've probably seen it before, and it pops up very often in mathematics. So what we do is we take our term 2 divided by s to the 5/2, and we write it as gamma of 5/2 divided by s to the 3/2 plus 1. But then notice that in order to do that, I have to both multiply and divide by gamma of 5/2. That's what you're seeing here and here. Okay, then what we're going to do, now the reason that I did that is that I have a formula on page 271 that tells me that if I know I know that t to the a is equal to the gamma function of a plus 1 divided by s to the risen to the a plus 1 power. So that's what I'm using there. Okay. So then, following along, what we do is we take the inverse Laplace transform of capital F, and now that is also linear, so we get this. And the important thing is, now look here, you see this 2 divided by the gamma of 5/3? Since this is a linear transformation, we can take constants in front of the transformation, and that's why you see it appearing outside of the linear transformation L inverse. And then from here to here, I'm simply looking at the chart, realizing that actually the inverse Laplace transform of 1 over s is 1, okay? And the inverse Laplace transform of this gamma of 5/3 divided by s to the 3/2 plus 1 is given by the following. It's just t risen to the 3/2. Okay, so then in the book they calculate, that's a half. They calculate gamma of 5/2. I'm just taking this right out of the book, and it's equal to 3/4 times the square root of pi. And so we arrive at our conclusion. Okay, so in the next section, what we will do is we will try to, section 4.2, we are going to be applying the Laplace transform to initial value problems. So there are some very powerful techniques in there that we will be talking about. So thank you very much. Bye.